You need to know these shape names and what they go to. To me, it's a little bit of combination of, yes, there is a little bit of memorization factor, but what I would encourage you to do is, in the memorizing, is visualize what these things look like. If you can see them in 3D space, their names make a lot of sense. They're weird, but they make a lot of sense. If you're not looking at what they look like and you're just straight up memorizing, it's really easy to mix them up. But yeah, when you take the test on this unit, you won't be given a list of options. Once again, it could be a multiple choice question, but if it was on the first response, you wouldn't. So flashcards is my recommendation for any time you just have to like get familiar with vocabulary and things like that. I'll post on Canvas some flashcards that you could just print, or if you want to make your own, if you feel like that would be beneficial to you, you could make your own from that. But I have some digitally you could print off and then use. Okay? Okay, let's go ahead and check through this. I'm going to point to it, and you're going to shout out your answer. Hopefully you sound the same. Ready? 1, 2, 3. This one is tetrahedral. What about the name tetrahedral helps me know this is it? 4. Tetra means 4, and this has 1, 2, 3, 4. Yep. Very good. Okay, count of 3. 1, 2, 3. Ben. Very good. Why is that little fella gonna be Ben? Yes, right? Let's draw it bigger. The little ghost here, right, pushes the bonds and makes it Ben. Okay? Now, just a disclaimer. The word ghost and how I'm using it, right, for bonding and stuff, is something I made up. So on the end of your AP test, if you're justifying a question, don't talk about ghosts. They won't know what, the graders will have no idea. Call them lone pairs. But I just like calling them ghosts because they help me visualize it. So, okay, very good. That one is bent. Okay, all right. 1, 2, 3. Trigonal planar.
Oh, trigonal. Oh boy.
Oh, I was saying
trigonal.
Okay. Now, a lot actually in B6, a lot of them were like T-shaped because it looks like a T.
No.
Which your Lewis structure does, but why does the molecule not take this shape? Yeah, right. It's all about repelling. And so it's a lot farther away to do, well, that's not a, maybe we should call it Y-shaped, because that's kind of what it does. Right, but that's the visualization here. It's like, okay, think of the Play-Doh, think of the toothpicks. How do I put them as far away from each other as possible? Okay, very good. Okay, oh, I did my numbering really strange.
Yeah.
Okay, number 4 is over here. 1, 2, 3, it is?
Seesaw.
Seesaw. Very good, right? Here's what it looks like. Why it's called a seesaw.
That one messes me up the most.
That one's harder to visualize. The 5 one I agree is like, I don't know if it's about 5, but once again though, why does this one not go tetrahedral? Because that's lone pair, right? So often the way I like do my visualization process is I always go off of how many domains it has total and then turn a domain into a ghost. So I would say, okay, well this has 5, so I gotta think of my 5-sided shape. Alright, so my 5-sided shape is this guy. And then, okay, one of them turns into a ghost. What am I left with? That's kind of how I like break it down when I can't remember. So, okay, very good. So this one's seesaw. Count of 3, shout out number 5. 1, 2, 3.
Trigonal.
Ooh, I don't know if I heard the right answer anywhere.
Uh-oh.
Is it trigonal pyramidal?
There it is, trigonal pyramidal.
Yeah, I got it wrong, but I brought it up.
Okay.
2 out of 5.
So once again, visualize what 4 looks like. So this right here gives you a domain of 4. right? So here's tetrahedral, but one of them is a ghost,
I'm pretty sure.
so that's where you get your trigonal pyramidal from. Okay? If by chance, if you're a very visual person and you feel like using these on like the homework, or like our lab that we're doing today, I don't have enough for like everybody, but if you're interested, I could like check some out to you if you want to take it home. If you feel like that would, if you're having a hard time visualizing these things, sometimes holding them can help in the visualizing. So, okay, very good. Number 6 is 1, 2, 3. Vent, yes.
Wait. Oh, let's go. I actually
So we have 2 types of vent. You have vent with 1 ghost, and now we have vent with 2 ghosts. Once again, you could think of, it is technically tetrahedral, but then 2 of the sides become ghost. So there's your vent molecule. Yeah.
So you know how like the lone pairs push them away?
Yeah.
So like how do they get pushed? Which way?
So, like, so I'll put it on like without,
So I'm probably thinking too much information.
and then maybe that's it. Yeah, so like this is, so those 2 ones are the ghost,
Right.
right? So they're
So
just,
they're already there.
yes.
Oh.
So that's why it really is. It still is a tetrahedral all over. We just can't see these. So the molecule itself we just call vent. So good question though. Okay, number 7. 1, 2, 3. Linear. Very good.
Yeah, I know.
Once again, think of building, right? You have 1 in the middle, 2 on the outside. That's it.
Process of
It's always going to be straight line. And number 8 is 1, 2, 3. Octahedral. Yeah.
Let's go.
So, any general questions? I know it's been like an eternity since I've seen you, so that's kind of why I was doing this quiz, is to wake up our chemistry brains a little bit. So, any general questions on that? Okay, so you can convert however many points you got on this into smiley faces.
Well, lucky person. Where is that? Oh.
It's like a very thorough process.
If you turned it in and there's nothing crossed off, it's because I didn't need to use them for you to keep your grades.
Do you want the quiz or should we just
There's your stuff.
I'll just swap those, swap those.
Okay,
Baba.
okay. All right, so here's kind of how we're adjusting in AP Chemistry with the new Term 2 schedule. Because we've lost 5 days of in-class instruction because of Wednesdays we're not here anymore. Which in chemistry is like so much in AP Chemistry. And I can't just drop things out of what I'm teaching you because then you wouldn't know it for the end of your test, which would be bad. Like, hey, I'm in general chemistry because I can just say, oh, well, they just won't learn that this year and life will go on. But for you guys, we can't do that. So here's how I've kind of adjusted to make up for those lost days. Because I also don't really want to have you learn. I like at home to be more just practice of what I've already taught you. I don't want it to be like, hey, here's something you haven't ever learned before type thing. So what I decided to make up those days is all of our tests this term we're actually going to take at home. Because technically we don't need to take them in class. I don't do anything for you. So that's something we can easily do like at home on Wednesdays. So that's kind of how it worked for the testings. And then so that actually helps because that gives us back 3 days because we have 3 tests this term. And then the other ones is we are going to do 2 labs that are virtual instead of in person. And I don't love it, but it was kind of a choice of, okay, do I either have them learn a lesson at home or do a lab at home? And so we're going to try the lab and see how that goes for now. But that keeps us on track where we're taking the Unit 4 test right before Christmas break, which I love having a test right before the break because then you can just go on break and forget chemistry for 2 weeks, right? And not have to do anything. So that's kind of how it's going to work. So for the Unit 2 test, it also gets a little scrunched here. After today, we will have finished Unit 2. Okay, so what I'm going to do is I will open the Unit 2 test this weekend with instructions on how to do it from home, and it will just stay open through next Wednesday. So if you feel ready before Wednesday, you're welcome to log on and take it. If not, take it by Wednesday. Wednesday is also when all assignments will need to be turned in because it's the end of the unit. So I'll have upload links for anything that we haven't had an upload link for yet. So, any questions on that? Pretty much how it will look, just for those that, some of you had to take the test at home last time anyways, or those that are at home always do it. But the multiple choice will just be through Canvas. And then the FRQ will be kind of similar to the retake last time, where you'll just write your answers down and then upload it. They will still both be timed, so I'll set up Canvas because our tests have to be timed accordingly. So, any questions kind of on that? Okay, pull out your note packet from last time, and let's kind of talk about what else these shapes can teach us. Is the first column filled in, like the geometry one?
Yeah, it is.
Okay, perfect. Okay, so we're going to talk about polarity, and then we'll go back and fill in the polarity column. So there's kind of three things we're going to be talking about today that we should be able to do on top of these pictures. The first thing, though, that we need to understand is that Lewis structures are key. If you can't draw a Lewis structure, you can't draw it correctly, you can't do geometry. And if you can't do geometry, you can't do polarity, or hybridization, or bonding. So if you're still struggling with Lewis structures, please reach out and let's get the help you need. Okay, this is a reminder, let's put all other homework or things we might have out phones away, and only have our note packet for today, so we're not distracted. Remember, your brain cannot multitask when it needs to think. Okay? I was thinking the other day that how amazing our brains are. Because with a toddler, you kind of see they have to they can't do two things at once. Because they're trying to figure things out. But it's just crazy how we get older, right? You can literally, I can be writing something and thinking about something else at the same time. Right? If I'm just copying something down, it's crazy. Our brains are amazing. So, okay. Let's review really quick. Can anyone by raising hand remind us? We did our little, that little polar bear and penguin comic thing. Can anyone remind us, what does it mean when something is polar? How do we find that, Bryce?
Unequal share of electrons.
Good, an unequal share of electrons. Okay, how's my piece, Bryce? I think of it, once again, as an analogy, as a tug-of-war. Okay, polarity is a tug-of-war of the electrons and someone is winning. If it's not polar, it doesn't mean they're not pulling on the electrons, it's just they're equal to each other. Another way you can think about polarity is, show you a picture here, you don't have to write this part down, but they are vectors, which is why I picked him. Does anyone remember his catchphrase from the movie?
Yes. Arrow with both direction and magnitude.
There we go. So a vector, if you haven't learned yet, you often learn in physics, I don't know in high school physics, but eventually physics or math. A vector is something with direction and magnitude, and polarity is a vector. So when we look at polarity, we got to look at both of those things. You have to look at the direction the electrons are being drawn, and how strongly they're being pulled. So that's the magnitude side. Let me go back to our picture over here. Okay, so I'm going to draw this down here because I made it, I actually did it yellow to that. Okay, so we're looking at carbon dioxide here. And the question is, we want to know if this molecule is polar or a non-polar molecule. The first step is you've got to look at the individual bonds in the cell. Now they're looking at the seal. Kinda. Or tape. Yeah, do I cut that part out, or do they just get to watch this part?
No, they're just gonna watch.
They just get to view everything. Yeah, they really do. Okay, we're back. Okay. So let's think about magnitude. Okay? How do I know? So between oxygen and carbon, who has a greater magnitude of the electrons? And how do I know? Who's going to pull the electrons away from the other?
Oxygen.
How do we know that? I see us all looking over there. What's the trend?
It has more electrons.
Good. The more, it's the electronegativity, which the farther to the right. Okay, so in that box up top where it says dipoles, draw 2 arrows showing the electrons are being pulled outward. Now, a dipole arrow, we put a plus sign on its tail, because if the electrons are being pulled away, it's going to be positive, right? But to determine the overall polarity, now you look at how these different dipoles relate to each other, how the vectors interact. Okay? If they are equal in magnitude and opposite in direction, okay, so if they have equal magnitude, and opposite direction, they cancel each other out. So the overall dipole is none. It doesn't have one. Because the individual dipoles have canceled each other out. Now, here's an analogy that helps some and not others. So if this is confusing to you, just forget my analogy, but maybe it'll help some of you. Okay? You can literally visualize it. Can I borrow you?
Sure.
Do you mind coming on screen? Is that okay, Gabby?
Yeah.
Okay, come stand right here.
Okay.
Matt, can I borrow you as well? Do you mind? Okay, so you can literally visualize it as a tug of war. Okay? Where, okay, I'm an oxygen, Matt's an oxygen, Aaron's the carbon. Okay, you put your arms out. Okay? No, not you now. So if we were, you don't have to touch her because of COVID life, but I think having the visual helps. If we were both to grab Aaron and pull with the same equal strength, is Aaron going to move anywhere?
No.
So she is a non-polar, not pulling molecule. That makes sense? If I have more magnitude than Matt does, though, because let's say instead of oxygen, I don't know, oxygen's like that. I'm fluorine, because that's the highest of them all. Which way is Aaron going to get pulled? Which means it's a polar molecule. So that you kind of visualize the molecule like literally like little tug of war people. If the middle person moves, it's polar. If the middle person doesn't move, it's non-polar. Now it is important though with my analogy, you can sit down now, thank you. It just helps if I'm not like doing it all myself, right? Warm my arms. What is it that's being pulled in polarity? The electrons, right? So we can visualize it like the atom, but keep in mind the atom's not the thing that's being pulled, it's the electrons that are being pulled. Now, here's what's key. So let's look at our next picture here with water. Okay? All right, between oxygen and hydrogen, who has the greater magnitude of electronegativity?
Oxygen.
Oxygen. So this time, so on those boxes up there, draw it going towards oxygen. where the significance of the 3D shape comes in. As a Lewis structure, it appears as if those dipoles cancel each other out, right? Opposite direction, equal magnitude, but, say it again, Bryce?
It's bent
It doesn't look like this, it looks like that, right? So, water has an overall polarity going in the upward direction. Now, you've got to be very careful with using the terms up and down, because up and down are relative to how you're looking at the molecule. So if you're ever using like directional terms without a picture for like FRQ, I would draw a picture so that the person reading can understand what you're saying. Or unless it has a picture. Because once again, you could draw water bent the other direction, right? And then in that case, it's going downward. But questions on polarity, how to identify it. Okay, let's do a check and see. Go back to that box of your practice problem. You talk to your table buddy about it and see if you can identify if it's polar or non-polar. Ready, set, go.
So Lewis structures like that. There's trigonal plane, which is there. It should be. It's gonna be polar or something.
Wow.
Because oxygen there's chlorine. Oxygen.
Yeah, because it would be,
Technically, they would be pulling too, but it's not equal magnitude.
So, is carbon more or less?
Carbon
Is carbon more, or does carbon have higher or less electronegativity?
Give me a pencil drop when you're done.
This one. Okay. So then these are polar.
I think this one is,
So these two are equal, but they're not opposite.
Yeah, technically, I wouldn't be going in opposite directions in the actual shape of it.
Wait, but since it's like this,
yeah, I think the two are.
actually, oh wait, this is would,
Right.
well, has to be equal
But then
magnitude.
oxygen
Yeah.
is still
Otherwise-
polar.
Two atoms.
Okay.
And so it would
They're
still
the
be
same,
Polar.
they're the same atoms, but they're together, so they're
This one
This is like,
they're apart from each other. But this is
So,
I think it was
all the
it
forms.
has the two straight up and then the three.
so chlorine has the most.
So it's like
So it's going
yeah.
up.
Yeah.
So I
But
think
then what
it's
about
just
the
trying to
two
show it as a three.
Yeah, I don't know.
But
I don't think that was actually.
so and I think they're all the same distance away from
Yeah.
each other. But so like all
You're
the
right.
same.
Because they're just sitting
But
there,
then
it's actually
there's
talking
no
to.
point this way.
So it would be not confused, they're all equal.
This way, so that.
So I mean, those ones cancel each other out.
And then.
okay, I'll give you in 5, 4, 3, 2, 1. Pencils down, let's check it. You can have a smiley face for each one you got right. This is a sign you're going to show me. If you think it's polar, give me a thumbs up. If you think it's non-polar, give me a thumbs down. Okay, that way I can kind of get an overview, a feel of how we're doing here. Okay, first one right there, show me what you think. Polar or non-polar? I think it is polar. Can someone put it in their own words of why you would say it's polar? Matt, go ahead.
So the two chlorines pull the same, so like they kind of cancel each other out because they're opposite directions of pulling. But then there's still the oxygen pulling up.
Yeah, so this is the case of where they're equally spaced. Technically, does it look like this?
No.
No, right? They are bent down, but this is a difference of magnitude, right? Oxygen has a higher magnitude of electronegativity than chlorine does, so you're going to have an overall shift towards the oxygen. So, very good. Questions on that one? Okay, show me your vote. Thumbs up or thumbs down for this guy? Polar or non-polar? interesting, we're like split. Like, all of you are saying one, mostly, and all of you are saying one. But it's polar.
Oh, dang.
So this is where visualizing the shape and getting the shape right is key. What 3D shape is this guy?
Seesaw.
A seesaw, right?
So it's
So-
not all of
Wait.
Here's your seesaw molecule. These two right here do cancel each other out in terms of their dipoles. Why do these two not cancel each other out?
They're not opposite direction.
Because they're not opposite in direction, right? Yeah, Evan.
So, if it has a lone pair, is it then it's automatically polar? Most of the time.
Most of the time. So yeah, there is a connection where generally when something has a lone pair, it's generally going to be polar because lone pairs make shapes
Mm.
not balance out.
Okay.
The one exception to that is the square planar, because since the two lone pairs are up and down from each other,
Mm-hmm.
and then the other four are cancel each other out, that one is not polar.
Okay.
The biggest thing that I'm glad to bring this up is in terms of justifying, just in case, for some reason, if the test says you have to justify why something is polar, hint, hint, okay, you cannot say that a lone pair makes things polar, because that's not a true statement. Lone pairs make the bonds unequal, which that makes it polar. But don't skip that middle step because it makes the sentence wrong.
Mm-hmm.
So, but that is a great, easy connection right away of like, okay, if something has a lone pair, it's most likely going to be polar. So, yeah, good connection. I'm going to have a smiley face for that.
Your thing is like different.
Yeah.
My picture's different than yours?
Yeah.
Oh, what the?
I don't know.
How did that even happen?
Oh,
Oh, that's strange. They're the same ones, they're just in different order.
yeah.
That's really weird because I normally make the notes and then I make the PowerPoint from the notes. Why would I switch them? Okay, this one, which I guess was your number 2. Show me your vote, polar or non-polar?
Pretty sure we don't.
Or wait, is that the one we just did?
That's the one.
Is that the one?
That's what we just discussed.
Yeah.
So you all answered for this guy. Oh yeah, because that one is T-shaped. Ah, okay, this one.
Okay.
Thank you for shaking out. Polar or non-polar? This one's gonna be polar. Now once again, if you get your 3D shape wrong, then it's gonna cause issues with your polarity. What's the 3D shape of that guy?
Square pyramid.
Square pyramidal, right? So you have your square pyramid. And once again, let me know at the end of the day if any of you want to borrow some molecule sets and we could trade off 2 later on if there's not enough, right? So here's your square plane pyramidal. One more on there. All the same. So in terms of dipoles, now that word dipole, once again, that's just describing like that arrow, right? The way it's going. So these 4 actually do cancel each other out, but there's nothing to cancel this one out with, right? So, questions on that? Okay, and this one should have been easy because I already answered it for you, but water is polar. So, do you got that one? Even though I already kind of told you the Questions on polarity? We'll practice it more on our homework, so if you're still feeling a little unsure, yeah, we'll practice it more and that will hopefully help. I'll also post on Canvas a simulation site you can go to that can show you things in 3D space with polarity, if that also seems like it would help you out. So, okay, any questions on polarity before we transition to hybridization? Okay. So, hybridization. I'm going to skip to some pictures because I think that makes more sense. So, first off, it's important to recognize that we could talk about hybridization for like probably 2 weeks to really understand it. But the number of questions that are going to be on the AP test about hybridization is maybe 1. So we're not going to spend 2 weeks on it. So this is kind of one of those topics that you might not understand all the way, but as long as you can answer the question, and I'll tell you what the question would look like, then you're good. And can understand it if you take higher level chemistry one day. I almost hate that they even put it on the test, because if you don't understand it, what's the point? But it's there, so I'm going to teach you it. Here's the concept, okay? Is that when things bond with each other, so let's say I have an atom that has an s orbital. So this is like electron configuration, right? The s orbital, the p orbital, d orbital. Okay? If I have an atom that has one s orbital and two p orbitals, scientists determined that when they bond, the orbitals become equal. And so there's this idea of them hybridizing. So they turn into, instead of these three, they turn into a hybridized sp2 orbital. So this funny looking guy is known as an sp2. It's a blend of these three. So notice that the number of orbitals stayed the same, right? 3 orbitals, still 3 orbitals, but now they're all equal in their distribution. Okay? So what we need to be able to do is, from a structure, tell what type of hybridization it has. But there's a very simple pattern to do so, and it's simply based off how many domains. Now keep in mind from last time, domains is like how many toothpicks you're using. Even if one of those toothpicks is a ghost. Okay? If something has 2 domains, we always give it a linear geometry. Now once again, notice the pattern of 2, okay? It has 2 domains, so that means the atomic orbitals available are 1s and 1p. When they hybridize, that's going to make 2 sp orbitals. So we would call it an sp hybridization. If something has 3 domains, that's our trigonal planar. Now, 3 domains, that means 3 orbitals, so it's an S, P, and another P. So when they hybridize, we end up with 3 sp2 orbitals. Are you seeing the pattern here? A little bit. So 4, that's our tetrahedrals. So that means we need 4 separate orbitals, so 1s, and then 3 p's. So we end up with 4 sp3 hybrid orbitals. For smiley face, what would you expect something with 5 domains to have for hybridization? Don't say it out loud, just think in your head. What would be the hybridization following the pattern for something with 5 domains? Evan, you have a thought?
Would it maybe be 5s2p3 because they need to fill up halfway? Or would
Say that one more time.
5 and then s2p3.
Ooh, have a smiley face because you're on the right track. Does anyone know why I won't ever have an S2? If you think back to our orbitals, the orbitals are the boxes with the arrows in them. And S is only ever 1 orbital.
Oh, I
Do you
thought it was an
remember
electron.
So,
Okay.
oh,
Yeah.
gotcha. But not a bad thought. Any other thoughts of what it might be?
We like P's 3 after F.
So S, P, 3.
And D.
Have a smiley face for that. If you also have that on your paper, you can have it as well. So, because the P only has 3 orbitals, so if you run out of P orbitals, then the next one you would go to would be theoretically the D. Now, if you wrote that on your paper, cross it off. Because science says it's not a thing anymore.
Anymore.
When I was in college, I learned about hybridized orbitals with the D shell. Now scientists aren't so sure that exists.
Why did they teach it if they didn't know if it exists?
I don't know.
I'm pretty sure they don't know a lot.
Because a lot of it is like, you know, I think it's just a matter of we learn more and we're like, because I think they just went off the pattern, so they thought it did exist. So when I learned it, but then with more information, now they're like, I'm not so sure if D's can hybridize. So anything past 4 doesn't have hybridization that we know of. So you won't be asked it, or if you are asked it, you just say NA, not applicable, right? Doesn't match, so. Questions on hybridization? Okay, let's practice. Flip back to your practice table, and with your table buddy, fill in that hybridization column. All you have to write is just SP, SP2, or SP3. You don't have to write how many orbitals there are, like 4 of them.
Trinomial crane.
You can just write that.
It's trigonal. Yeah. Alright, so this is 3 SP10. Okay, next one is trigonal binomial pyramid. And then this one is 4. No, it's 4. Tetrahedral, so 4 SP equals 4 times That's 5.
Give me a pencil drop when you're done. Did you make it?
Oh my god.
I didn't think it was, I wasn't sure. Okay, everyone ready? You have a smiley face per one you got right. Oh, what? Yeah, I figure we need lots to start off the And you have 5 less days to earn smiley faces, so. No.
So just give us triple the amount each day.
Since we lost 5, we might as well triple it.
Yeah.
Yeah, that makes sense. Okay, I can go back to that this way. Here we go. Okay, this molecule right here has sp2 hybridization. No, technically no. If you did, it's still right, but it's just not necessary. Because sp2 is always 3 orbitals, so. But you're good if you did turn it that way. So, questions on that one? Yeah, so if the question is what is the hybridization of this molecule, you can just write sp2.
Is that the same for all of them?
So this one you should have not applicable, because they're both above 4. Water, you should have sp3. Questions on that? Once again, the biggest thing, so here's what we're looking at, everybody. Give your lovely faces this way. You're just counting out how many things are around it. So for water, look at the central atom. It has 1, 2, 3, 4. So that means you need 4 letters to hybridize. So that's why we have 1 S, 3 P's, adds up to the 4. So, questions on hybridization. That's like what the questions will look like if you see it. It'll just say, what's the hybridization of this thing? So. Good so far? Okay, last thing. That's the SP3 one, by the way, just like what it looks like, and how they hybridize. Okay, the last thing we're going to talk about is this idea of how they bond with each other. Okay, so we have 2 types of bonds, and they describe the type of overlap that is happening. Okay, so we have what is known as a sigma bond, and then we have something known as a pi bond. What you need to be able to do is, given a molecule, you should be able to identify how many sigmas it has versus how many pi bonds it has. Okay? So first of all, let's understand what they are, and then we can identify where they go. So a sigma bond, the way I visualize it, is it's a direct overlap of the orbitals. Okay, so this, if you want to label it right here, this right here, that's a sigma bond. The Greek sign for sigma looks kind of like that, like an O with a hat, kind of. Okay, so that's a sigma bond. This is also a sigma bond, and this is also a sigma bond. A pi bond is when two p orbitals overlap, like their little butterfly wings are touching, but it's not in the center. Okay, so this right here, this is a pi bond. Okay, that's kind of what they look like. I forgot to put my balloons.
Oh, it's actually pot.
Improvised. Okay, let me show you this and I'll go through it. Okay, so in a single bond, the first bond that atoms always make is a sigma. So a single bond is always a sigma bond. Because the first way they're going to bond is directly overlapping with each other. But after you do the first direct overlap, the second bond has to be a pi bond. So in a double bond, you have one sigma and one pi. Because once again, if you visualize it, right, so the sigma goes like this. I need more arms to demonstrate this, right? Then the next bond has to go somewhere else, so it goes around the sigma bond. I have us demonstrate together, but that kind of breaks like COVID rules. We were all like touch each other.
Just put a bunch of hand sanitizer on.
Yeah, I guess that's true. A triple bond is going to be one sigma and two pi bonds. Okay, once again, thinking in 3D space, okay, it's like take a picture of my hands and I'll move them. So here's your sigma, that's there, okay? So now the first pi can go like this around the sigma. So you still have your sigma in the middle, right there, right? And then the second pi can go like this around the next. So a triple bond has a bond here, here, and in the middle of the sphere. Everyone kind of see how that looks? This is once again why a triple bond is so strong as well. It's because of how much. Do you also see why this is why a quadruple bond, like where else are you going to bond? Right? Like if you have a bond here, here, and here, there's no other space for the orbitals to overlap. Here's kind of some funny pictures that kind of show it. So here's it like separate, and then this is showing like the blend of it. So there's your sigma bond in the middle, and then the two pi bonds form around it. Questions on sigma or pi bonding? Okay, I'm for one more or two more spine faces today. I'm going to draw a Lewis structure on the board, and you're going to tell me how many total sigma and pi bonds it has. You don't have to draw it yourself, just count on how many it has total. Okay, ready for this guy?
It's not as hard as I thought.
I just gotta wait till you're all done.
Along with that.
Yeah. Oh.
I was gonna copy it on my paper, but
It looks really great though. Good job.
Thank you.
it just keeps going.
Oh geez.
Oh
Okay.
my gosh.
Almost
Not
done.
about this.
What molecules?
Oh geez.
Wait,
Keeps
a
going.
bond on top of a bond, you're going the opposite.
Okay, I think I'm done.
Okay.
Okay, count up how many total sigma and how many total pi. And then write it in. You don't have to draw the molecule in this.
I think I need to like cross it off and stuff.
14.
This is a chemical structure for caffeine, fun fact.
I got 14.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
Set your pencil down when you're done.
Wait. 19, 30.
Oh, no.
Wait, no,
I guess that is the benefit of having it
15.
on your own paper.
What?
Note to self, put this on their paper.
Look, count.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
60. I counted it 3 times.
I counted it 3 times.
It's 6, it's 60.
or whatever. Alright.
Okay, ready to check it? I think we're all understanding which is the big key here.
Yes.
So, sigma bonds are in every bond. So first step, just count how many bonds there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. If you said 20 sigma bonds, you are correct. Okay. Now pi bonds are in a double bond, and there's one of them. So now you just count your pi bond, or your double bond. So we got 1, 2, 3, 4. So 4.
That's
You
not
got
as
one
hard.
smiley face for sigmas, one smiley face for
Let's go,
pi.
I got one.
Questions on identifying sigma and pi?
I get it now. 100%.
Okay.
Whatever the best one is.
Any other questions? Okay, I'm like very behind. So, 2 assignments for tonight is you need to finish the homework 2.7. You were supposed to do the Lewis structure, the Lewis structure and the Vesper for it, the geometry, but we left the other 2 columns blank. So finish that and check your homework. And then, the second thing, and this is gonna be a good thing to kind of an overview of almost everything in this unit, is what I'm calling our Vesper lab, okay? So, this right here is our Vesper lab, I'll pass out to you. First thing that you should notice, or be aware of, is it is counting as a lab. I did a lab like this in college, so if they can call it a lab, I can call it a lab. That means we can put it in our lab binders. But that means in your grade, it's going in as a lab, which is a lot more than an assignment. So if you're going to pick and choose, pick this, okay? Also, because it's a lab, I am gonna give you a week before it's due, so it's not due till next Friday. So even though the test is on Wednesday, I will let you turn this in till next Friday. I'd recommend doing most of it before then, because it will help you for the test, but it's not due till Friday. Also, with it being a lab, I'm not gonna post the answers. But if you send it to me, like email it to me before Friday when it's due, or even like on class in Tuesday, if you want to show me really quick, I can let you know if you're doing it right or not. But I won't post the answers for it. So, question, Bryce?
Do we have to write a lab report?
No. So for this lab, there's no lab report, just this packet. Okay? Pretty much, once again, it's having to do similar to the homework with a few added things. You're doing Lewis structure, geometry, hybridization, polarity, bond angles, and then sigma and pi. So kind of connecting it all together. Once again, I try to do this as much as you can without your notes too, because that would be a great way to test yourself for the test.
Do you have to have bond angles like memorized for testing?
Yeah, because you could be, once again, it's kind of one of those things where like, I've only seen it, like, it's only gonna be one question probably, like for the end of year test. But yeah, yeah. That's where though, once again, if you can visualize the shape, a lot of them are very logical. The only one is like tetrahedral, that 109.5, which is kind of random feeling. But all the other ones kind of, but yeah, good question. Any other questions? Okay, so we got 12 minutes to work. So your options are either to work on the 2.7 or you can start working on this. Okay? But until there's 1 minute left or you're done with both of these, we shouldn't be doing anything else.
Can I go?
Yeah, go ahead. Yeah.
When you're finding hybridization, you count the electrons. Right?
Yes.
And then, is that kind of like the lone pairs on the outside?
No.
Okay, that's what I'm trying.
Yeah, so domains are only based off the central one.
I was like, I